All right, thanks for coming. Welcome to Design and Rendering Strategies for Blockbuster VR Games featuring Batman Arkham Shadow. Before we jump in, I've been asked that you all please silence your devices, and with that, we'll get moving. My name is Ryan Darcey. I'm one of the design directors at Camouflaj, and we just shipped Batman Arkham Shadow in October of last year. And the game did pretty well, so we're here to talk about why we think that is. As stated in the title of this talk, we've got both a design and rendering section. I'll start with the former, and then I'll hand it off to my colleague, Kevin Call, to talk more about some rendering magic. More specifically, I'll be reviewing some of our Manta Mantras, with Manta being the code name for Batman Arkham Shadow. These mantras help focus our efforts over the course of the project, and we ended up with over 50 of them. But I'm just going to focus on the ones that I think are most relevant to development in VR, and also relevant for ones that are about translating high-profile IPs to VR. So I'll kick it off with our first mantra, keep it authentic Arkham. It was very important that Arkham fans perceived Arkham Shadow as a new entry to the Arkham series. We knew that translating such a beloved IP into VR was going to receive a lot of heavy scrutiny. With that in mind, anytime a teammate had questions about how something should play, look, or sound, my question back to them was, how did the previous Arkham games do it? In almost all instances, we aimed to reverse engineer all the design choices unless we had to deviate because VR. And of course, there was a lot of that as well. That said, when it comes to developing a sequel, I found that it really helps to balance your innovation between new, better, and the same. Keeping it the same meant keeping it authentic Arkham. Making it better was where we selectively tried to improve upon features from the original games, and there were a few of those instances as well. But we also had some guidance on making things better from the Arkham Trilogy's original game director, Sefton Hill. In a DICE talk from 2012, Sefton discusses Arkham City development and suggests that when you've got a great feature, make it better. This is essential if you're trying to reach best-in-class quality. You've got to keep pushing, pouring more time and resources into great features so that they can reach legendary status. Every AAA experience requires a healthy serving of these IP-defining features. That said, this will likely lead to some scheduling problems, and Sefton's got another reminder to help us there, which is features we don't do are just as important as the features we do. On Arkham Shadow, we specifically lost some really cool gadgets like the remote battering. This played surprisingly well in VR and beat all of our expectations for how comfortable it was to throw the battering and transition the camera directly into controlling it. But it was absolutely the right decision to cut it because we didn't have enough campaign to show off that feature, and we spent more of our time making great features legendary. The last category from our balanced innovation slide is about creating brand new features. And this is where we felt the most pressure to flex our creative muscles. And for the most part, deciding on where to spend our new bucks was driven by capitalizing on unique VR opportunities, specifically leaning to the Quest 3 strengths and squeezing as much as we could out of the hardware in order to achieve experiences that are just not possible in any other medium. One of Quest 3's strengths included phenomenal controllers and their high-fidelity tracking, which helped avoid some of the clunkiest, most immersion-breaking experiences I have in VR, which is gesture fails. On Arkham Shadow, we aim to make gesture input just as reliable as button input. Can you imagine if players of console games had their button press fail 1 out of 10 times? Totally unacceptable. And we felt that pressure to make sure that the gestures in Arkham Shadow were just as reliable. Grabbing and throwing the battering received a healthy amount of love for this reason. And while we're on the topic of player sentiment, we embraced an easy-to-learn, difficult-to-master philosophy in service of everyone needing to feel awesome. The Arkham games are not exclusive to hardcore players like a Dark Souls, and the broader gaming audience is still migrating over to VR. So if you want to make a game with mass appeal, I think at least for the time being, you've got to make it really accessible. Related, another mantra we had was deliver the fantasy, not the simulation. There's probably a really cool simulation-heavy Batman game out there, but I don't think it's an Arkham game. And I don't think it's going to be widely embraced in VR at the moment. As an example, we started with a more simulated version of the grapple gun. You had to first lift up your hand, press the button to start aiming, release it for the line to launch, and then tug your hand in order to launch yourself forward. It actually was a really cool VR experience on its own, but when you put it in the greater sandbox, there was just too much friction, and we ended up reverting to a more traditional, simple reticle always-on experience and a simple button tap to launch the player. Another area we diverged from simulation was in our environment interactions, where we embraced the idea of making physacs, not physics. The way this primarily surfaced was by having generous autocompletes on interactions as soon as we had enough feedback to detect player intent. So this lever for the door here, as soon as we detected the player nudging the lever down a little bit, we slammed it to the full down position in order to avoid a kind of in-between states where the player thought they finished it but didn't complete it. Speaking of abusing the laws of physics, we leaned hard into a very locomotive combat feature set. When the team was asking me how we'd pull off Arkham's iconic free-flow combat, my answer back to them was, Batman doesn't walk across the room, he punches across the room. And this simple guideline ended up laying the foundation for combat, including an off-screen counter that auto-snap-turned the player to an off-screen enemy when they were being attacked out of view. Baking locomotion into combat actions was essential to deliver on Arkham's free-flow combat. And I would argue presents a much more heroic experience, as the player can then fully focus on making the combat gestures with their hands and not fiddle around with analog sticks trying to get from here to there. While we're on the topic of combat, perhaps one of the most controversial choices we made was leaning into a highly orchestrated Beat Saber-inspired combo system. At the end of the day, I think the bet paid off. Leaning into simulation-heavy experiences often leads to a lot of janky experiences in combat. We needed to demonstrate that Batman is equal parts strength and grace. Restricting the player's strikes to these more orchestrated combos allowed us to ensure both that the gesture flow felt good and that the enemies responded with an impact worthy of Batman's armored fists. Another critical combat-adjacent area to highlight is the Predator feature set. And we got help here from another Rocksteady veteran who worked with us on Arkham Shadow, Bill Green. He introduced us to the idea that Batman is never the underdog. In combat, that meant the ability to take on upwards of a dozen enemies at a single time. And in Predator, that meant always having ample perches and a full arsenal of gadgets at your disposal. Delivering on this feature-rich demonstration of Arkham's sandbox was essential for selling Arkham Shadow as a real Arkham game, but in VR. Another mantra that Bill brought us was, if it looks grappleable, it must be grappleable. That was important for Arkham Shadow as well, but we had another variant for VR, which is, if it looks climbable, it must be climbable. In general, if the player can't read the environment and can't judge what is and isn't interactable, it's going to lead to a really frustrating experience. I can't prove this with science just yet, but I actually think fundamentally that inability or ability to read the environment can lead to a lot of physical discomfort. So in addition to things like making sure you've got a high frame rate and never rotating the player's camera, ensuring that what the player expects to happen actually happens leads to a very comfortable VR experience. All right, I've got one last mantra to bring a close to our Bill-isms, which is, like Rocksteady, we make bold iterations. This meant that we had to be fearless about trying new things and then ruthless about throwing out things that didn't work. This led to some pretty scary moments, butting up against some important deadlines, but I think you need a balanced, healthy amount of risk in order to really reach that blockbuster VR game status. All right, on to something completely different here. Another critical non-action component to the Arkham franchise are the investigation moments. Early on in the project, we sought to really blow out this feature set and involve a lot more challenging detective moments for the player. This led to a lot of player confusion and ultimately messed with pacing and messed with the player's expectations of what an Arkham game is. Ultimately, we reverted back to a more traditional Arkham investigation complexity with the guiding mantra of keep it simple, sleuth. I would often joke that we need to deliver something on the order of a reading comprehension test for a 5-year-old. And that led to our unfailable multiple choice pop quiz moments, which were the only addition that we made to the investigation sandbox. All right, plowing ahead, let's talk about the player's full body avatar, or FBA as we called it. A mantra we embraced here is the player's avatar is the sum of its unequal parts. Most importantly, you got to make sure the gauntlets and the hands are super high quality for the FBA. Going from there, you got to make sure there's a really nice chest with a nice batarang, and then lastly, showing some legs during some opportunistic moments like sprinting, sliding, and jumping. Another big goal we had for our environments was delivering spaces on the scale of Arkham Asylum's courtyards. We knew that in order for the player to really feel the excitement of grappling and gliding around the map, that we had to have more of these expansive spaces and bravely and smartly embrace big. Ensuring that your hero environments like this properly complement your gameplay, absolutely essential to blockbuster moments in VR. An underlying mantra that helped us deliver on those large environments was this guidance from our art director, Matt Core: emphasize the significant and streamline the rest. This was absolutely critical for delivering a game at an Arkham scale and quality on the Quest 3 chipset. We had to be very selective about where we spent our art bucks, which also informed our lighting scheme and shadowy environments. Very on brand for Arkham Shadow, and something Kevin will be diving into detail here soon. A mantra that then helped us determine what to streamline was the game is your boss. What we were explicitly trying to avoid here was any one personal bias or one discipline or one feature taking an outsized amount of room in the game. We aim to evaluate the game holistically across all features and all disciplines. So when we had questions about whether we should do X, Y, or Z, I often said, let's let the game tell us. From there, it's all about listening to player feedback and figuring out where you should lean in and where you should cut back. Another point we had here was we would often get hung up on like a bunch of hypothetical pitfalls, which led to our mantra, troubleshoot prototypes, not ideas. You can spin yourself in circles for hours, days, or even weeks, imagining all the ways that your features may break or be terrible for the player experience. The best way to sidestep that is get it in the game in its most simplest form and evaluate from there. This was our approach for the shock gloves, which Arkham fans loved from Arkham Origins, but rightly called out as OP. Instead of talking about it for hours, we just tried a bunch of different variations and ultimately found something that fit all of our non-OP needs. Another cornerstone at Camouflaj is making meaningful games, which informed our say something important mantra. This mostly applied to our writers, of course, but was also an invitation to the team to support and elevate our narrative through environmental storytelling, music, and player interactions that complemented the core narrative themes. This rage sequence highlighted here in the image that starts with the brutal interrogation in Monarch Theater and ends in Gotham's courthouse. It was a great example of how gameplay, story, art, and audio all came together to focus on a key theme in our story, rage. Speaking of stories, remember that all of us in this room get to write the VR rulebook. This medium is still in its nascent days, and it's important to test its limits and break down imaginary walls. It's when you push these boundaries and develop never-been-done-before experiences that you truly deliver a blockbuster VR title. And with that, we're in the design portion of this talk, and I'm going to hand it off to Kevin to talk about some rendering techniques.
Thank you, Ryan. Hello, everyone. My name's Kevin Call, and I'm a rendering engineer at Camouflaj. Today, I'm going to talk about some of the rendering techniques and strategies that we use to make a gorgeous game with Arkham Shadow while staying within the performance constraints of the mobile chipset of the Quest 3. First, I'd like to share some background info about the project. We made the game in Unity and shipped with a custom version of 2022.3, and we use Vulkan for our graphics API. We use a custom render pipeline, and our target frame rate was 72 FPS, which equates to a frame time of about 13.89 milliseconds. Let's start by talking about baked lighting. Because of performance constraints, the vast majority of the content in our game uses baked lighting. For static objects, we use Unity's built-in directional light maps. With directional light maps, you have two textures, the light map itself, which stores color and intensity, and the directional light map, which stores the dominant direction. Here's a visualization of the baked diffuse light from the light map. Directional light maps allow normal maps to affect baked lighting. You can see this in action with the embossed letters on the sign. And here's a visualization of the dominant light direction. This is what the scene looks like when lit with directional light maps. It's nice, but it's missing something very important, direct specular. Without specular, it's very hard to express many surface types, like metallics or smooth, shiny objects. Fortunately, the solution was fairly simple. We evaluated our specular BRDF using the dominant direction when applying light map lighting. While it's a major improvement over having no specular, there is a subtle issue with this approach that's easier to see in another example. Here's a screenshot from a different location in the same scene. The specular lighting looks good here, but notice the clear separation between light and shadow. What happens if we look at this from a different angle? As you can see, there is now strong specular lighting in some of the shadowed areas. This looks wrong because there shouldn't be a direct light source affecting just the shadowed areas like this. The reason this happens is we are naively assuming direct light is responsible for the light in the dominant direction at each texel in the light map, when in actuality, many of the texels are predominantly lit by indirect light. So now the question is, how can we further refine this to avoid false positives? The solution we arrived at was to use luminance as a heuristic to predict whether the light at a given texel in the light map was predominantly from direct light. We construct a mask from the diffuse luminance by allowing artists to specify a minimum threshold along with attenuation. This is then multiplied by the specular in the shader to filter out false positives. To be clear, the mask is not a separate texture, it's calculated on the fly in the shader. So let's go back to what the problem looks like, and then see what it looks like after the fix. Notice how the false specular highlights disappear from the shadowed areas. The way we gave artists the ability to tune these parameters was with the volume system in Unity's core RP library. This system is excellent for passing parameters to the GPU based on camera position. Before we move on from light maps, let's take one last look at the first screenshot from the scene and layer in the improvements. Here's the scene with just the built-in directional light maps. And here it is with specular from the dominant direction. And finally, with the correction to remove false positives. Now let's talk about baked lighting for dynamic objects. For dynamic objects, we use Unity's built-in light probes, which store spherical harmonics, commonly just called SH. Like with light maps, by default, you don't get any specular from light probes. You can see an example of that here on Batman's arm. We also added specular to the SH lighting using the dominant direction. Though in this case, the dominant direction is calculated from the SH coefficients. One problem that our artists encountered is that it was sometimes difficult to balance placing baked lights for both the static environment and dynamic characters. Here you can see that while the lighting is fairly realistic, it's a bit hard to distinguish Gordon from the background due to the darkness. Our solution to this problem was a system called custom probes, which allowed us to override the SH for characters using a material property block. Here you can see how we embellished the lighting from the nearby red light to help Gordon stand out a bit more from the background. Individual custom probe components could be placed as needed to override character lighting. Artists were able to intuitively add light to them using a 3-point light setup. An added bonus of this system is it allowed for very quick iteration, since artists could immediately see the results on screen without having to regenerate baked lighting. Now let's talk about real-time lighting. As mentioned previously, due to performance constraints, we seldom used it, though there were specific cases where we did so carefully to further enhance the visuals. As we based our lighting off of URP around late 2020 and early 2021, we used forward rendering with a per-object light list. Here's some results from performance tests we did on Quest 3 at GPU level 4 by rendering a full-screen quad using one of our most common environment shaders. As you can see, the cost scales linearly with the number of lights and at an even higher rate when using shadows. Unfortunately, forward rendering is especially poor in games like ours where we have to combine objects into large meshes to reduce draw calls. Let me illustrate why. Here's a screenshot from one of the Predator scenes from our game. In the actual game, this uses all baked lighting, but I'm going to use it as an example to demonstrate what would happen if we were to start adding real-time lights to it. This visualization shows which objects are affected by real-time lights. As there are none in the scene currently, all objects are gray. This is what it looks like if we add a real-time spotlight. Objects colored yellow are now paying the performance cost for the light. However, you can see that the light is only affecting a small number of pixels on screen. Even if it touches just a small part of the object, you pay the full cost of the light over the entire surface. Now we've added another spotlight on the left. You can see how some additional objects have turned yellow, but more importantly, some objects that were previously yellow turned red, indicating that they are affected by both lights and will incur an even higher cost. Though we generally avoided real-time lights, we did use mixed lights in key cinematics to improve character lighting. Mixed lighting is essentially a way to bake some part of the lighting and do another part in real time. Unity has multiple mix modes, but we exclusively use subtractive. In subtractive, direct light is added to static objects in the light map and to dynamic objects with real-time light. Indirect light is added to static objects in the light map and to dynamic objects with light probes. The nice thing about mixed lights is since they only apply real-time light to dynamic objects, which are generally small, it is relatively easy to ensure that no more than a single mixed light affects a given dynamic object at once. Here you can see how only the dynamic objects in the scene, a character and a grate, are highlighted yellow. indicating that only they are paying the cost for real-time lighting. Now let's look at how mixed lights improve the quality of lighting. In this example, you can see what Leslie would look like if the key light in the scene were baked. With a baked light, both the direct and indirect contribution are stored as SH in the light probes. It's not bad, but it looks a lot better with a mixed light. Notice how much better the contrast is between light and shadow on her face. This is because the direct lighting is now being applied in real time. And it looks even better with soft shadows enabled on the mixed light. This is the configuration that we used in this scene in the actual game. Another issue we noticed is that we pay for the overhead of the light loop in the forward pass even when there are no lights in the scene, which unnecessarily increases register pressure in the shader and adds performance overhead. To mitigate this, we conditionally compile out the loop based on the presence of and types of light in the current frame, then use a global shader keyword to select which variant to use. The logic is as follows. If there's at least one real-time light, we need to enable the loop for all objects. If there are only mixed lights, we only need to enable the loop for dynamic objects. And if there are no lights, then we disable the loop for all objects. Now let's talk about real-time shadows. As discussed previously, mixed lights allowed us to add shadows from dynamic objects to other dynamic objects, but we also wanted a way for characters to cast shadows on the static environment. And we wanted to be able to have several shadow casting lights in the scene at once. Because of their issues in forward rendering with large mesh combined objects, actual real-time lights with shadow weren't an option. Subtractive does let us use a mixed directional light to add shadows to the static environment, but this isn't helpful for indoor environments. What we really wanted was a solution for spotlights. Playing Arkham Asylum inspired us with a possible solution. We noticed that they appear to be using multiplicative blending to composite dynamic character shadows with the static environment. In this screenshot, you can see how Batman's shadow darkens the shadow of the bars instead of merging with them as you would expect. This led to the birth of what we call fake shadows. The basic idea was to apply the fake shadows in a deferred style. First, we'd render the shadow maps. Then we'd render opaque objects with forward lighting. Then after this, for each fake shadow light, we'd render a projection volume, sample depth, and use this to reconstruct world position to sample the shadow map, and return an attenuation value, which would be multiplicatively blended with the frame buffer. Finally, we'd render transparent objects at the end. This approach had several potential perf benefits. It avoids any additional lighting calculations, diffuse or specular, and it's completely decoupled from the forward pass, which means less register pressure, and the cost would scale with the screen size of the projective volumes independently of anything else. But there was also a performance drawback, which is that we'd be adding extra overdraw for the projective volumes. The only way to know for sure if it was a net savings was to test. But before we could test, there was another problem we had to solve, which is that when we were developing this technique in early 2023, there was no way to read depth in Unity without making a copy of the depth buffer, which is especially expensive on tiled GPUs. Tiled GPUs do allow you to read depth at the location of the current fragment efficiently, and this is possible in Vulkan, but it wasn't exposed at the time in Unity. Since we weren't sure when this feature would be available to us, we came up with a backup plan, which was to use our existing decal system instead of real-time projective volumes. It works by creating a new form-fitting decal mesh from source meshes in the scene. Because all the computation to generate these meshes is done at edit time, at runtime, they're just ordinary meshes, basically. After making an initial prototype, we tested how the performance compared to an actual real-time light with shadow, and the results were very positive. Even in the case of just a single light, fake shadows came out ahead, despite the extra overdraw. And we already knew that they would scale much better than real-time lights as the number of shadow lights in the scene increased, so we decided to move forward with this approach. We implemented fake shadow lights as modified real-time lights to take advantage of Unity's built-in shadow rendering. To prevent Unity from using fake shadow lights for lighting, we simply don't add them to the light index map that is populated each frame. We also store a reference to the light's associated decal mesh, and we use a specific layer to ensure only certain objects like characters would cast fake shadows. it was important to use an ordinary layer instead of a rendering layer, since the rendering layer test is not performed in the function calling_results.getShadowCasterBounds, which returns a bool to allow us to early out of shadow rendering in the case that there are no objects to render. Earlying out allows us to avoid inefficiency. We can avoid unnecessarily drawing the shadow decal, and we can avoid unnecessarily allocating space in the shadow map atlas. To improve the workflow, we added the ability to create fake shadow lights from existing baked lights. And we also made it so modifying the spotlight angle or range would correctly modify the decal projective volume. During the last year of the project, we finally got the ability to efficiently read the depth buffer in Unity. And though it didn't make production sense to go back and change how the existing fake shadow lights worked, we were able to expand the system to use depth read to project Batman's iconic shadow while gliding. We also used depth read to add multiplicatively blended blob shadows to characters' shoes to help ground them even in situations without fake shadow lights. We generated 3D SDF textures for the shoes and then sampled them with object space position reconstructed from depth to get nice fall off. Finally, let's talk about reflections. As a foundation, we use Unity's built-in reflection probes, which store a capture of the environment in a cube map. While reflection probes work well in perfectly box-shaped rooms, problems start to occur in scenes with more complex geometry and varying lighting conditions. For example, in this scene, you can see bright green reflections on the trash can in the dark corner, making it look out of place. To solve this, we implemented a technique called cube map normalization. You can see that with this technique applied, the reflections more accurately match local lighting conditions. To implement this technique, we store the SH at the point of the reflection probe capture. Then in the fragment shader, we scale the reflection using the ratio of diffuse lighting at the fragment to the diffuse lighting at the reflection probe sampled with the vertex normal. If the diffuse lighting at the fragment is darker, then the reflection becomes darker. Likewise, if the diffuse lighting at the fragment is brighter, then the reflection becomes brighter. If you're interested in learning more about this technique, consult these presentations from Black Ops 2 and God of War. Give you guys time to take pictures. Cool. We also use what we call reflection proxies to augment the reflections from probes. A proxy is an image captured of a specific object in the scene at edit time. At runtime, we then render them reflected over a known reflection plane to a screen space buffer, which objects can then sample. In this screenshot, notice how the neon sign sticks out from the wall and reflects in the puddle. This wouldn't work well with a probe since they essentially flatten the reflection to the surface of a cube, but the proxy allows the reflection to poke out of the wall. A problem we encountered with proxies is that they could leak through solid objects. In this example, we added a proxy along the back wall to improve the reflections on the water, but the reflections could penetrate the boat and make the water look very bright under the dock. To solve these sorts of issues, we added the ability to render occluders to the screen space reflection buffer, which would block proxies from rendering. And that wraps up our presentation. We hope you learned something that you can apply to your VR games. And if you have any feedback, be sure to scan the QR code on screen to let us know how we did. And since we don't really have time to do a traditional Q&A up here, we'll be hanging out just in the lobby, so feel free to come up and chat, ask questions, whatever.
We might have time for one question.
Oh, do you want to try one question? Okay, we'll be in the hallway. It'll be casual. All right, thanks, guys.